letting us participate in this, Lisa. My name is Kevin Borders. I'm with Alpha Technologies, and today we're going to talk about powering oDAS networks. We'll do a little background on DAS in general, but spend most of the time talking about indoor DAS. The agenda for the topic today is we'll do an introduction of my company, as well as the topic in general. Talk about our experience in DAS power applications. Provide an overview of the topic, specifically focus on active indoor DAS, because active systems are the ones that require power. And then we'll talk about iDAS power solutions, different options for local and line power, and then at the end we'll talk a little bit about Alpha-specific solutions in this space. Alpha is a industry player for power systems, both AC and DC, and renewable energy. We are a provider of equipment, power system equipment, for macro cells, DAS, and small cells in the wireless space. A provider for wireline power, such as central office and broadband systems, fiber to the home, security, public safety, traffic, transportation, smart grid, renewable energy, sort of the whole suite of power conversion technologies. We've been around since the mid-'70s, over 35 years, and have quite a bit of experience now, actually over a decade of experience in the world of powering DAS. To sort of set the stage, considering the diversity of the audience, let me start by saying we're familiar with a macro cell. The macro cell tower that we all know and either love or hate if it's in our backyard. But it is typically a device that can handle thousands of connections, multiple technologies, multiple carriers or frequencies. It requires lots of backhaul, lots of bandwidth for backhaul. And because it's so important in the network, there's redundancy in the components in terms of the power system and the backup and battery reserve behind the power system itself. Because these things, at least when they're in a cage out in the open, the physical space is not as big an issue, although there's some constraints because of the cost of rental, but it's not typically a big issue. And quality of service is very important. By quality of service, that's basically making sure that the system operates continuously. Contrast that with a distributed antenna system. They're obviously much smaller than a macro cell. They're being deployed and have been deployed to provide both coverage and capacity. So they're providing coverage for sites that or areas where the macro cell can't reach, and they're providing capacity to take care of the issue with the bandwidth demand that's created by all of the smartphones and tablets that are on the market today. DAS is used both indoor and outdoor, and there's a lot of difference in the way those are deployed. And I'll touch on outdoor just briefly, and then we'll talk about indoor. They require significant traffic if you think about where these are deployed, whether it's in a convention center, a hotel, a shopping center, or a sports venue. There's a lot of traffic, at least for bursts of time, and so they handle quite a bit of traffic and require a lot of bandwidth to do that. They can address multiple technologies and also single or multiple service providers. So there could be 2 or 3 or 4 different wireless service providers all operating on the same DAS network. There are some physical space constraints because of where these go, specifically with the remote devices, because they're going to be in the public eye, and so you don't want them cluttering up seats and taking up a lot of, and being visually unattractive. There are some issues with the remote devices. Because there are so many of these relative to the macro cell, and because of they're an augment in many cases to the macro, cost is a big constraint in these relative to the macro cell. And then lastly, the focus on these is quality of experience, and by that is not so much quality of service. These do not necessarily have the same amount of battery reserve or redundancy that a macro cell has, but they have to have some level of ongoing service so that the end user has the same quality of experience, whether they're on the macro cell or on the DAS network, so that it is a seamless event, if you will. So with that, let me just give you a quick background on our experience in the world of DAS. We've been doing this, as I said, for several years. We have powered DAS systems that go into stadiums and baseball ballparks and stadiums, casinos and hotels that you see down on the bottom left. We've done the Aon Center in Chicago, which is a tall building on the left, and as well as some other big shopping venues. And then we've also powered the New York City subway system in Grand Central. So we've had a lot of experience in understanding how DAS works, both indoors and outdoors, what the requirements are for the venue operator as well as the integrator. Alpha has strong relationships with our customers and with the OEMs that participate in this space. So whether it's Bell Canada, AT&T, Verizon, any of the service providers that you see, as well as the companies such as TE Connectivity and Corning and CommScope, who are all providers of DAS equipment. One of the things that we've done to try to set us apart as a company, because of our sort of pioneer role in this, is that we've taken a thought leadership position in this. We've been on the cover of OSP magazine. We've been prominently featured at the DAS and Small Cell Congress of Speakers. We've developed a series of introductory videos, short videos, that are available on our website to view on what is DAS. We've written a short chapter-based white paper series on how to power indoor DAS, and we've created tools like calculators and configurators to help with understanding how to set up the equipment and the network based on distances, cable gauges, etc. So we've been at the forefront of these this thought leadership, and look forward to continue to be there as we go forward. Now, to just dive into the topic and talk a little bit about DAS, this diagram, if you will, shows a stadium and shows the circles are meant to show the different DAS serving areas from the remote nodes that are inside that stadium. Typically, the way this works is whether it's indoor or outdoor, there are multiple carriers or service providers that connect their base stations to the DAS equipment. If you look at the bottom of the slide, the boxed-in area is in essence trying to represent in a very basic way the DAS equipment. So you combine the RF signals that are coming in from the base stations that are owned by the various service providers. That RF signal in turn gets converted from electrical to optical, transported over an optical cable. At the remote end, it's converted back from optical to electrical, and in turn connects to a remote node or antenna and an RF power amplifier. So that, in essence, is sort of the simplistic block diagram of how the DAS network works. Multiple service providers, or it could be one, but it's generally multiple service providers, all riding over the same transport out to antennas and having their signals broadcast out and distributed out from those antennas simultaneously. Now, there's a couple of kinds of indoor DAS. There's passive and active. Passive uses coaxial cable that connects from a head-end device up to remote access units or remote nodes. We're not going to focus on that because we're really focused on power, and powering these remote nodes is really where the issue is in the DAS space. So we're going to focus on the active indoor DAS network. And in this case, you can see down in the bottom of this building there is a head-end equipment. That head-end equipment connects via the fiber cables up to, in this case, it shows a remote access unit being deployed on every floor. And I went through this on the previous slide, but the way it works is that the RF's converted to optical, transported up to the devices, converted back to RF, amplified, and then connected via coax to the antennas. And obviously, when you're going the other way, then the process is reversed. So the key is that there's going to be a couple of different areas we're going to focus on: powering the stuff that's in the head end, down in the basement of the building, and then powering the remote access units or remote nodes that are up on the floors. So in the head end, there's a few devices, and this varies depending on the equipment vendor. But in general, there's a main interface unit, optical converter unit, system controller. You've got to account for battery recharge time because you're going to have batteries and battery backup. And then you also have to allow for future growth, at least with regard to your power system. On the other end of this, there's remote nodes. There's either the access units where it's at the very edge of the network, or in some cases hub units where you distribute out to those access units. In either case, you're providing power for both the head ends and the remotes. At the head end, there's not a lot of power typically required by the DAS equipment. You can see over in the right-hand side, which is the little relay rack, you can see the system controller and the optical converter and the main interface unit and all. You know, you're talking in this case somewhere between 100 and 400 watts altogether. And so generally that's going to be powered by some shelf power system like you see down at the bottom, which simply supplies 48 volts. It's, you know, you bring in AC, convert it, and rectify it to 48 volts, and distribute that 48 volts up to those devices. Not a lot of power required. However, in some cases, DAS equipment is powered by the same power system that powers the base station, particularly in a situation where the service provider is providing the DAS. In that case, you're going to need a larger power plant, a DC power plant. And let's see if I can show you a picture of that. On the right-hand side is something you would see like in an MTSO, you know, a mobile switching center, or potentially a smaller version of this in a DAS head end, where you're powering both the base station and the DAS equipment. If you're only powering the DAS equipment, then you're probably going to be able to use one of the power systems that you would see over in that rack on the left-hand side. There's actually 4 different unique configurations that are displayed, ranging from 100 amps up to, say, 260 amps of power to power those the DAS-only equipment. Now, I went through that sort of quickly because the powering the head end, albeit essential, isn't particularly novel. It's something that, you know, we do in the rest of the industry where we're supplying 48 volts with battery backup, typically in a standby or portable or access to a portable generator. So it's a very robust system. It's very commonplace. But I did want to at least touch on this and let you know what the head end look like. Now, when we switch gears and look out at the remotes, you can see on the left-hand side there's some different photographs of different remote nodes or remote access units, and you can see that the power consumption for each of these ranges somewhere between 80 watts and 450 watts, depending on the configuration. You can see that the single input, single output kind of arrangement, ISO arrangement would be, say, up to 80 watts, whereas a minor arrangement would be more likely up to 450. Now, I can say that those numbers are moving north, and so there's actually more power consumption for newer devices as we move forward. So the numbers will inch up from 80 and inch up from 450. When it comes to powering the remotes, there's two alternatives. One alternative is local power, and the other is centralized power. Let me talk for a moment about what local power means. Local power means that you've got an AC outlet somewhere nearby the remote node. You may do that and not provide any battery backup. So that would mean that in the event of an outage for whatever reason, the remote node would be disconnected and would have to go through a reboot cycle and to come back online. Another local power option is to take that same AC outlet, connect a standard commercially off-the-shelf UPS that provides a little bit of backup to power these remote nodes. Now, I can say that the top two, the AC, just the basic AC without backup or the AC with a UPS, they used to be the prevalent means of powering these devices. But over the years, what's happened is there's been a transition from AC powered devices to DC powered devices by the vendors. And so one of the options for local power would be, instead of using a UPS, if you have a DC powered node, be to use a rectifier or a rectifier plant, somewhat similar to the ones I showed you in the panel previously with the different ranges of sizes. The good thing about the rectifier is that it enables you to configure different battery backup. So if you had a very important site that you wanted a few hours of battery reserve as opposed to a few minutes, you do that simply by changing the amount of power and the number of strings of batteries. Now, that's the local power option, but there's another option that's centralized power. And the centralized power approach uses the power that you have back at the head-end equipment to deliver current to the remotes over copper cables. That is typically referred to as line power. And we'll talk about that in quite a moment. First, let me, first let me talk a little bit about the local power architecture. So you can have, as I mentioned earlier, at the head end you have your power plant, conventional 48-volt system. And out of each of the remotes, you're going to have whatever local power solution we elect. Here's some of the key attributes of this. First, there's an AC outlet required at each remote node. Now, from an RF planning standpoint, there's not always AC outlets available where the node needs to go. So the choice is, do you put the node where the outlet is, or do you hire an electrician to put the outlet where the node is? Typically it's the latter, but obviously that's an expense as well as a logistical issue to deal with. There's power conversion and batteries required at the nodes, assuming that you provide some level of battery backup. And I can say that most companies today do provide battery reserve of some sort, just to make sure that they're covered in the event of any sort of surges or hiccups in the commercial utility AC feed. But by doing that, you provide power conversion and batteries at each of these sites. So a power conversion is either a UPS for AC or a rectifier for DC. So that means you have equipment, as well as you have to enclose it in a cabinet that's secure from the public, or it goes into a telco equipment closet, which again would be mounted in a rack, again secure from the closet. In any case, it's taking space, and if you're using it in the enclosure, then you have to deal with the issues about aesthetics and all, because you don't want it to be an eyesore for the public. The thing I mentioned previously is that as we go forward, and it's been the case now for the last, I don't know, few months, 18 months or so, that the vast majority are now becoming DC-powered remote devices. So here's some of the issues with local power. As I mentioned earlier, the access to AC power is not a given, so you're either mapping your RF to the AC outlet, or you're putting the outlets, or hiring somebody to put an outlet in where the RF is. If you don't provide battery backup, you risk alienating key customers. Let's face it, you're putting the DAS network in because you're trying to please a certain segment of your customer base, whether they're the people going to the football game or the people doing their shopping or what have you. You're doing this for a specific reason. And so in doing that, you want to make sure that you're not going to drop off the call as they lose AC from the local utility. The third thing is that when you make the decision to provide some level of battery backup, that means you have to provide the batteries physically at those sites, which leads to a proliferation of these throughout your network at the edge of the oDAS network. And these batteries have a cost associated with them, and of course they have to be maintained because batteries have a certain lifespan. Then the last thing is, as I alluded to a little bit, the size and location of the power conversion equipment. You have to be careful. That picture, which I don't know how well you can see it, but it's a telco closet that was not really designed according to spec. As you can see, it looks a little bit like a rat's nest. So let me talk for a moment about centralized power. And this will be where we really focus the rest of the talk. In this instance, all the power conversion and batteries are supplied at the head end and not at the remote. In fact, there's no power provided at the remote for the average circuit. The copper cable actually delivers power from the head ends and energizes the remote nodes and provides a current. As I mentioned earlier, that they typically require DC power, so nowadays, and so that's perfect because the power system is supplying the DC power. The head-end power system is a DC device. By doing so, this eliminates the need for local power conversion, the batteries, and the enclosures. Now, if you take a look at this diagram, you see the yellow line is fiber, and the dark line is copper. And most often, people are installing these indoor DAS networks that are line powered. We use a composite fiber copper cable, which are readily available in the marketplace today. By doing so, there's an increase in the cost of the equipment, of the cabling, but there's only one labor cost for actually pulling the cable. Excuse me. So there's some special requirements for indoor applications, and these special requirements are due to the fact that this equipment is in the public venue, deemed to be potentially accessible to the public, and so there's rigorous safety requirements put into play by the National Electrical Code and the Canadian Electrical Code. Now, there's some specific challenges with centralized power, as I mentioned earlier. You've got incremental cost because you've got a cable copper to each of the remote units. You also have to protect the public from this cable because it's a power cable now, although it's DC. So you do that by using armored cable, and that will make you compliant with the standards. Or in some cases, you may use conduit, and specifically when you're having to go through walls and things like this. The other thing is that you have to use certified electrical personnel or a certified electrician in order to certify the installation. So all of these things add cost to the indoor application using line power. So why does it matter? As I mentioned, it's the money issue first and foremost, because while we're trying to get away from the proliferation of batteries, the local power equipment, the fact that you have all these devices and all this capital involved in this equipment, on the other hand, this line power seems like it would increase the cost because of conduit, armored cable, electrician cost, etc. So one of the things and one of the goals that we've embarked on and the industry's looked at is how to power these devices using conventional surface-mounted cable. By doing so, that can avoid the cost. You don't have to use conduit. You don't have to use an electrician. The cable can be pulled by a conventional DAS tech, and the equipment can be installed by the DAS technician as well. So there's a way to do this, and the way to do it is to use a special type of circuit identified by the National Electrical Code or the Canadian Electrical Code as a Class 2 circuit. Let me explain that for a minute. A Class 2 circuit, in essence, less than 60 volts DC, and the power on any cable pair is less than 100 VA, or 100 watts, since the DC circuit. Now, one of the phrases from the NEC's book is that a Class 2 circuit is considered safe from a fire initiation standpoint and provides acceptable protection from electrical shock. So what we're seeing is that using these Class 2 circuits takes away any of the issues with safety. And as you can see from the second bullet, you can do it using conventional surface-mounted cable, which means that you don't have to have conduit or armored cable. Then lastly, because you're doing a Class 2 circuit, you do not require the authorization of a certified electrician. So what this means is that for indoor DAS applications to be effective with line power, then you have to find a way to employ these Class 2 circuits. So let me explain how that works. First, we're going to start with the head-end equipment. Now, a couple things about the head-end. You have plenty of power, plenty of batteries. You're already powering the DAS host equipment. You may be powering the base stations, as we said earlier. It is very reliable. It has N+1 redundant rectifier so that the power plant will continue to operate even if a rectifier fails. There's parallel battery strings that enable you to extend the amount of battery reserve. There's typically a standby diesel generator, so that will provide service during extended AC outages. And the head-end equipment is routinely maintained typically, and certainly are going to be maintained, more likely to be maintained on a routine basis than equipment that's distributed and at the edge of the network. So the way this works is that you add line power equipment to the head end, and that line power equipment takes the bulk 48 volts from that head end power system and distributes it evenly out over multiple cable pairs out to these remotes. Now when you do this, remember each of these cable pairs is limited to 100 watts according to the NEC requirements for Class 2 circuits. So that means that the nominal distance when you do this amount of power that's required by the remote. Now you can extend the distance a little bit further, quite a bit further actually, by boosting the source voltage as close as you can up to 60 volts. So one of the things you do is you include DC-DC converter technology and boost the voltage up to 57 volts. And that gets you close enough. 57 is typically a limit. It's got a couple reasons. One is because of tolerances. You don't want to get too close to 60 volts and for tolerance purposes accidentally go over that level, which of course would put you in violation of the NEC. and it's also used for certain other applications like GPON. So 57 volts is the DC-DC output. What that does is that doubles your distance effectively, roughly doubles your distance to about 1,600 feet. So now from the head end out to the remote, you can go 1,600 feet using this line power equipment. Now, we'll talk about that for a minute because we went from 48 to 57, but I said we doubled the distance. So there's a couple of things at play here. First, when you're doing the 48-volt distribution without the DC-DC conversion, that distribution is distributing the output of the DC power plant. When the rectifiers are offline because of an AC outage, that means the batteries are providing the DC output. So the line power equipment would be distributing the voltage from the battery. And batteries will operate typically all the way down to 42 volts. So what that means is that instead of designing your network at 48, you really have to design it at 42 to allow for this battery cutoff issue. So when you have a DC-DC converter in line with the circuit, you're no longer designing at 42, but you're designing at 57. You can see from the graph that the way DC-DC converters work is that for a wide input range of, say, 42 to 60 volts, they have a constant output. So even if the batteries are dropping near their cutoff level, you're still putting out a 57-volt output, which means that's what you designed to. The other reason that the distance effectively doubles is because the losses in the cable are not linear because of the what's known as the I²R function in cables. So as the current squared times resistance, and so as the current increases, the amount of distance you can go significantly drops. So that's the reason, and the numbers are roughly 800 feet if you don't have the DC-DC conversion, 1,600 feet if you do. Now, before we go into any details about how the products work and how this works, a question has to be, why not just use a traditional fuse panel? And there are integrators and companies that have done this, and there are some companies that make fuse panels that are touting them for this application. And one of the reasons it's attractive is because fuse panels are very inexpensive and very common. The 48 volts is distributed through the fuse panel and sent out multiple directions. And the amount of power is limited by the size of the fuse. And so you can say, well, I can keep my power under 100 watts because by making my fuse selection. However, UL and CSA require that the 100-watt limitation be met when the primary protection is bypassed. So that means that the fuse is not in the circuit at all. So if you don't have a fuse to do the protecting, then you no longer have a guarantee that you won't be in excess of 100 watts. So what does this mean? Well, what it does mean is that a traditional GMP fuse panel will not meet Class 2, not in and of itself. It also means that you can use them, but you can only use them if you're going to put your cabling, either armored cable or in conduit, and have the instrument certified by commission. Obviously, when you think about a oDAS network in a large venue, anytime you start talking armored cable, conduit, and then adding on the cost of the electrician, it doesn't take too much of that before any benefit you get with the fuse panel material offset. And typically your business case blows up as soon as you have to use this conduit. So let me dig in for just a minute about the Alpha-specific oDAS solutions. We have a product that is called the eLimiter Plus. The eLimiter Plus supplies 57-volt, 100-watt Class 2 circuits to the remotes. As you can see, it has a modular arrangement. So each of those devices with the little green lettering on them is a module. Each module has 4 Class 2 circuits on it. So in a 19-inch shelf, there are 9 of those. So that would mean that a 2-rack unit high or 3.5-inch tall, 19-inch wide shelf could supply 36 of these 100-watt circuits. Now, in our case, each of the circuits includes both the current limiting that's needed to meet Class 2 and the DC-DC circuitry, so that we're ensuring a constant 57-volt output as well as Class 2 compliance. The other thing I'll mention is that on the far left side, you can see there's a little controller. That's one of our standard Cortex controllers that is used in our power plants, our 48-volt power plants, and it is included in the shelf and enables remote control and access of the device. The efficiency, by the way, of the power conversion is greater than 92%. And as I mentioned earlier, you could centralize this device and radiate out 1,600 feet in multiple directions to reach your remote device. But there's got to be a question now that says, well, this sounds good, and 100 watts makes a lot of this device makes a lot of sense as long as my cables or my loads are less than 100 watts. But what happens when your loads are greater than 100 watts? Well, we developed a device called an aggregator. The aggregator has 8 inputs, which are 8 Class 2 inputs, and produces 1 bulk output. So you can say that this one device could take up to 8 inputs and output, say, up to 800 watts of power, or slightly under 800 watts of power. Now, the interesting thing, though, is that the NEC says you cannot parallel Class 2 circuits. So in layman's terms, let's talk about it like this. You can't take the Class 2 circuits, twist them together out at the remote node, and say taking 2 of them, automatically, and voila, have 200 watts of power. That's a violation of the code. And it's a violation because it's possible when you have a fault to introduce a greater than 100 watts of power on the return leg of the line. So without getting too deep into that, what I can tell you is that the way they have ruled is that if you have an end-to-end system, so that there is Class 2 circuits exiting the device at the head end, the eLimiter in our case, and entering the device at the remote end, and the device at the remote end provides all the proper isolation, then that system can be certified as Class 2 compliant. And that's what we've achieved with our eLimiter Plus and Aggregator. Now, I can tell you that this little Aggregator device is a small unit. It's a 1-rack unit high, 8 by 12, as you can see, and those mounting ears can be moved around so that you can mount it either in a rack or on a wall. Here's what an application would look like, and this is just a sort of a rough view. There's 3 different situations where there are larger remotes. At the top, you see a 450 VA remote, which would take 5 circuits. On the right-hand side, a 350, which would take 4. And down at the bottom, a 225 VA load that would take 3. In each of those cases, we had to use the aggregator in order to, and multiple cable pairs feeding that aggregator to power those remote nodes. All of the others are simply 60, 80, 50 VA loads, and this is just for illustration purposes. So in this case, if you added all this up, we're using 18 out of the 36 available circuits. But the point is to show how an eLimiter Plus can power smaller remote nodes that maybe have a small coverage area, as well as larger devices, which may either be used in hubs or to power a much larger space, say, for instance, an atrium space, as opposed to the end of a hallway or end of a floor on, say, a hotel. So we believe that line power has many advantages, and some of those include the elimination of the batteries at the remote site. We've seen this. We supply both types of products, so we've seen both the local and the line power solutions. And the line power has gained a lot of traction with our carrier base, and the reason is because not only is the CapEx analysis better for line power, but it's also much better because they're avoiding all the operational expenses due to the battery maintenance. The other thing is it makes it much simpler because you're eliminating AC power at the remotes. So you no longer have to deal with the logistics of coordinating with the electrician, nor do you have the cost of the electrician. It's much simpler to install this because you're simply running the composite cable out to wherever your DAS nodes are, your remote nodes, so you don't have to deal with any of the power interface devices out there. And then lastly, this line power technique improves reliability. If you think about it, your network now is as robust as your head-end equipment or head-end power equipment, which is typically very robust because it employs a belt and suspenders method of providing power for the head-end equipment, in that it has N+1 redundancy, battery strings, and multiple battery strings, and standby generators. So unless your cable gets cut, which in this case, of course, you'd lose communication because your fiber would be cut, your remote nodes are going to have all of the same level of reliability and resiliency as your head-end equipment. So with that, we've taken the approach that says you can now say goodbye to remote batteries in these applications. We've seen this over the last couple of years, and this has become a trend. And just wanted to thank you for the opportunity to share this with you, and turn it back to Lisa and see if there's any questions.
Thanks a lot,
Thanks, Kevin.
Mike, can we hear you?
Hello, can you hear me?
Yes.
Not sure what happened before. Thanks,
Just
Kevin.
going to turn it over to you right now. Mike?
Hello?
Yeah. Go ahead.
Yeah, Lisa, do you have any questions at this point?
I just have one question. There hasn't been any submitted. If anyone has any that they'd like to send in right now, you can go ahead. Just one question that was submitted on registration. Approximately how many watts of power are used by an antenna in Wi-Fi systems in subway tunnels, and how is it supplied by a Cat6 cable or power cable?
Okay, that's a great question. Wi-Fi access points are typically going to be, less than 25 watts. They could be powered using the technique that I just mentioned, but more often than not, they're powered with power over Ethernet. Now, power over Ethernet, and by the way, using either Cat 5e or Cat 6 cable. There are power over Ethernet or PoE injectors, and they vary depending on the size and the number of ports. But let's say that each port of the injector supplies 30 watts of power. There are devices that are as big as 25 ports. So that's a 750 watt device. So in that case, if you're doing it with indoor power like we talked about here, you would have to use the aggregator, power the PoE injector, and the PoE injector would in turn power the downstream access point. If it's an outdoor application, and sometimes the subways, it goes either way, but the subways that we've dealt with are typically outdoor, then in many cases what you do is you provide a local power supply that is robust and large enough to power the injector as well as any other equipment that's nearby.
Okay. One more question, and I haven't had any submitted, so if there aren't any submitted, this will be our last question. How prevalent, referring to your presentation, how prevalent is this power scheme? Is it in use? Is it mainstream?
Yeah. Oh, yes, it is. It is. In fact, it's been adopted by some of the larger service providers as their preferred method of powering indoor DAS. It's been enabled over the last few months with the advent of the Aggregator, where we now have addressed essentially all of the issues with indoor power. In the past, we could do, anything under 100 watts, but now with the Aggregator, we can address the larger nodes as well. And so it is being used prevalently by the major service providers, and one of the largest service providers said that they did the comparison of line power to local power, and the line power was I think their quote was a slam dunk winner every time. So as I mentioned, we do both. We do local and line power, but since our customers think that line power seems to be the slam dunk winner, that's the reason we do the webinars on the line power.
Okay, we have had a couple of questions. Maybe that one spurred.
I actually have a follow-up to that one, Kevin. Line versus local, what's the installation time difference between the two? Is there any impact either way? Just for getting a project up on the air, just wondering.
It's quicker with line power. We've not ran any studies, or I don't have access to any studies yet. But the line power is typically going to be quicker. A couple things. One is your requirement for line power, in addition to providing the line power equipment there at the head end, is you've got to pull cable. And you're pulling the cable anyway, right? You're going to pull fiber to each of the remotes. And so if you use a composite hybrid fiber copper cable, then your labor time is essentially the same either way. So once you get the cable pulled, you're ready to connect to your remote nodes. Contrast that with the local power, where you are dealing with the electrician, with the building, getting permits for the AC, installing the power conversion equipment, and then doing in addition to pulling the fiber cable, and then connecting all of that up to the remote node. It's a great question, and we're looking at doing some studies on this so that we actually have some data to back up the sort of anecdotal information I gave you. But it's clear that the line power approach is going to take up much less time and much less cost in terms of installation.
Great, thanks.
Great. So there are a couple more questions. The first one to come in was, how does the head-end distribution get connected to power at the venue?
Okay, the basic head-end power equipment is going to connect to is powered by AC. That's a rectifier plant that's powered by AC. And so that's going to come off a house panel, and it's going to depend on the amount of power that's required as to the size of the power feeds that are coming in. Think about this, similar to in terms of the breaker panel in your house. If you're talking about how does that device in turn connect to the eLimiter type product, you would come off the distribution of that 48-volt plant and run a 48-volt and neutral, or 48-volt and return leads over to the eLimiter and connect them at the eLimiter. So just two feeds from your basic power plant. So I hope that addressed the question.
Okay, thank you. If it doesn't, we can always follow up afterwards. If anyone has any following questions, just email them to me. There are a couple more now. The next question is, can local solar panel power and controllers be incorporated into your power/battery designs?
They could be, but remember, we're really talking about this being used indoor, and so it would take a unique application where solar would make a lot of sense. And I mean, you know, perhaps some sort of atrium kind of arrangement. And I'm not sure that it's going to be very economical. The other thing you have to contend with is if you can have solar, you've got to have some sort of panel. And one of the things on indoor is, when it comes to indoor DAS systems, is you're oftentimes dealing with a venue owner's wishes. So you want to be careful that you adhere to their wishes and make sure that you're aesthetically pleasing in order to win their favor. And I'm not sure if you start putting panels and all, you may end up with a perception of cluttering the installation. Assuming, of course, you had the right installation for that to work in the first place.
Okay, thanks. There's one last question. What's the power handling capacity of eLimiter?
I have to do the math in my head, but it's an eLimiter shelf. Has 9 of those cards. So that means it can produce up to 3,600 watts. 3,600 watts means that it's going to require an input power of about 4,100 watts. And the reason I say that is because it's 92% efficient, so you lose a little bit in the power conversion. And 4,100 watts is roughly 80 amps of power coming from your power plant. So I think if I understand the question, if you're going to put in an eLimiter in the head end, then you have to have an additional 80 amps of rectification in the head end, or you have to have that amount available.
Okay, thank you. And as I mentioned, if anyone's questions were not answered, please just send me an email and I can introduce you to the right people at Alpha to get the answers, including Kevin. So Mike, do you want to say a quick, since you can speak?
Yeah, just to wrap up, thank you very much, both Kevin and Kurt. Really appreciate that. Great informative session. As well, I want to note that this, as well as other DAS webinar series, have been recorded. They are on our YouTube site. You can search YouTube Alliance Corporation, and it'll take you to the right place. As well, any further information on the Alpha systems we were talking about today can be found on their website. And I know it's a bit long there, but you can also search and just Alpha and DAS and distributed antenna systems, and it'll come up as well. And again, thank you, Kevin. Great job. Appreciate it.
Yes, thank you, Kevin. Thank you, Michael. Thank you, Kurt. And as I mentioned, I think I may have mentioned, this webinar has been recorded, so I will be sending out a link following up to the email with, I will be sending out a link to the webinar recording so that anyone can watch it whenever they like. And if you would like a copy of the presentation, please send me an email and we can get that to you. Thanks again for participating, and look for the next one in the new year. Bye-bye.